So let's continue with the supervised segmentation approaches. Before, we just with the k-means, we just let the algorithm find the segments based on the data without knowing any ground truth or anything like that. With the supervised segmentation methods, we actually will have some ground truth data to train our models, and that gives us different ways to do it. We are going to look at different methods, also pipelines, how to do the processing to help us to have a flexible workflow. And there is some material to read. Actually, to be honest, I have to check these links again, but I think some of them are at least reliable still. Again, we have a lot of new modules, a lot from scikit-learn, and later we'll also have TensorFlow in the modules that we load. But in principle, what we have is that this supervised segmentation is based on two steps. One is a training step where you teach your model what outputs it should provide given some input. And once we have done that, we can do a prediction telling if you provide some input, predict what kind of class it should be. And the important thing is that the training phase, you have the training with the ground truth, and the prediction uses new and unseen data. And we have methods for classification, regression, and both. And depending on how we combine them, we can achieve different results. So starting with the classification, we get back to the blobs again. And this time, our blobs will actually have predefined label. So in this case, we create 3 blobs with 3 different colors, which we will use as training data. And the first algorithm that comes to mind when you start doing supervised learning is the k-nearest neighbor. And in this case, it's about looking at the neighborhood or the closest neighbors and say that given my neighborhood, I say I'm in this kind of location. So for these 3 hikers, this one, when he looks at the trees in his surrounding, he says, yeah, this is a pine tree forest. Nice. The next one says, depending on how many trees he consider, he would say it's a birch forest, or it's a mixed forest, or something like that. If he only looks at one, the closest one, I believe, is the pine, and then he misses all these two trees. And this one, he says he is in a birch forest. But depending on how many of the trees he looks at, the decision could be different. And that is the concept also of k-nearest neighbor. You are looking at, with the current point, you're looking at the neighborhood point in the trainer data, seeing what is the class of each of my neighbors. And the majority class is the one that gives you the answer. So, if we have this cluster, we can see I have added 3 points. You have the dot, the plus, and the cross. And the plus is pretty obvious. It's the green class. The orange dot, if you look only at one neighbor, you would say it's a green one. However, if you start looking at more neighbors, say 3 neighbors, then all of a sudden you say it's the purple one. So this one is more ambiguous, and depending on how many classes you select, you get different answers. This one, even though it's remote to both the green and the yellow, I think actually it's more towards the yellow. And if you would take more points into consideration, it would be more and more clear that that one belongs to the yellow class. And this is the way how this algorithm works. You fill, in principle, a training data set with a lot of points, and then the prediction is just done by computing and finding the nearest neighbors. You can also do it with text. So in this case, we have values 1, 2, 3, 4, which is associated to I am a dog. When we do this fitting, we just add two vectors in here. We have an x vector, we have an I vector, and then we get this kind of response from the training. And if we try with the training inputs, that's exactly hitting the choice, then the output would be I am a dog. However, if we now would put different inputs, so some more random values, we have here 1.2, 1.5, 1.8, and 100. Then the first one, which is 1.2, would give the response am, because 1.2 is closer to 1, which is associated with am. And 1.5 is still closer to 1, and then it also gets am. And then 1.8 is closer to 2, then it becomes an A. And 100 is, even though it's far away, it's closer to the dog, so that turns into a dog. So the long outliers, they always relate to the endpoints in the training data. So let's go back to the blobs, and we have a little bit more overlapping in this training data. You can see that there are green dots in the purple and purple dots in the green, and then we have a mixing zone between them. So let's see what happens when we try to run the k-means. Again, we do the fitting. We have only one neighbor in this training. And as we see, we have this mixing region, and of course, that also causes our training data, the test scan to also give a very confused impression in this region where there is an overlap. The test data is, in principle, we just generated a matrix with all coordinates, and we threw it on the predictor, and it gave us these results. So if we increase the number of neighbors, so now we have 4 neighbors instead, then that actually helps us to get a more smooth transition line. There is a little bit confusion down here, but in general, it's more reliable if you increase the number of neighbors. And that is to be expected in principle. Unless you have a complete mix of everything, then you are anyway lost. Another way of training is linear regression. Fancy name to say that it is a supervised machine learning method, because regression is something you do in the normal math classes pretty early. But anyway, it is also in the context of the machine learning package. And the basics example, you have an x and y array, some points, 1, 2, 3, 10, 20, 30, 40. And then you let the regression run, and to be expected, you get the slope and an intercept, and it matches nicely when you run this prediction. But let's try with some other data points. What happens if you had this as training data? If you put in an x equal 100, you would get minus 990, which still matches. So it extrapolates pretty nicely in this model. What you should be careful about still is when you take points outside of the data, you have to be more and more careful how you trust them. In particular, if you have polynomial data, it can be nicely fitted within the data points, but outside it can run away in extreme values. So be careful there when you do when you look beyond the training region. So we can also do regression on our data points. We have these x and y points, again, a different blob set. And we have two groups, 0 and 1. And it looks like this. And here we can also do a regression. We have the x and y points and these categories. And when we run it, we compute, we get slopes in 2 dimensions because we had 2 coordinate vectors and some offset. And when we look at this, we can see with our test points that we have a gradient, but before we had just 2 classes. And if we make a little bit more detailed, we get this continuous image, which also has an obvious gradient. It may be a bit confusing at this point, but if you would, yes?
But so the slopes are like two linear curve in the 2 dimensions?
You have a linear plane.
I see, okay.
So it's just how the plane is tilted in x and y. That's the 2 slopes. But you can see that the gradient has a direction which you could actually somehow also see in the data that you have. And if you would put a threshold on the fit, you can actually see a very nice segmentation line between the two groups. So that is a jump between the 2 class, discrete class, and the continuous fit value. Yet another way to look at the supervised classification is to use decision trees. And when you say trees, normally you think about something with the leaves towards the sky and roots in the ground. But in computer science, the tree is flipped upside down, so you have the root in the top and the leaves going down. So that is how it has been traditionally drawn in computer science. And we want to do a decision tree classifier based on some numbers. We have here, we want to identify odd numbers in the sequence. Some sequence, in this case it's 0, 1, 2, 3. And we let this be fitted within the tree, where we have the input numbers and what they are supposed to be. And here we say first that we have a split. If it's, let's see, what is a split? Let's see which values we have. We have here, we have only one sample, and the value is 1, so then it's odd. And then we take the rest of the values in this one, and they are split again. Then we have the, this is confusing now. The values, this is just 2 and 2, and that's, now I got confused with this tree. Yeah, so here you have a selection. If it's less than or equal to 0.5, then it goes in here. If it's, the split is here, 1.5 splits here. So between 1 and 2, that means this one is, the 2 goes here and the 1 goes here. And here you have 2.5 is a split, and then you have, if it's not fulfilled, then it goes here, and if it's fulfilled, it goes here. So you always have decisions on some kind of threshold value. This is a quite basic example, and this Gini factor is a value that was developed actually in economics, looking at the income level of a population. And when you have a low Gini factor, then it's very unbalanced. And if you have a high Gini factor, it's balanced. So that is also used as a selection criterion in this case. So let's try to bring in the blobs again. That's the original blobs, I think. With 3 groups and train the tree. This apparently turns into this kind of tree. I'm not going to look exactly in it, exactly what it's doing, but apparently it splits it into 3 different classes. And you have category 1 has 34 dots, category 3 actually has 33 dots. And the last category, the middle category has 33 dots. So it's a pretty balanced tree when you come to the number of dots. And when you have run it and run the test points, it splits the data in this way, which makes sense in a way, but it's maybe not what you have wanted to expect. In particular, if you looked at the k nearest neighbor, then we had a split across here. Now it's very more boxed. And this is a little bit, the reason is that the tree is looking at the one coordinate at a time. So first maybe it looks at x, separating in this direction, and then it looks in y and separating in this direction. And then it's splitting it that way. To get rid of a little bit of this effect, you can use something called a random forest. And that means we create a lot of trees on different parts of the training data. And then we use majority voting to select which tree decides the class. And with that, we can do much more complicated data. So you see here, very strong overlap. And now we can see how it behaves. So let's try a forest. In this case, we do 5 decision trees with this test data and see what happens. First of all, if we look at one tree, now keep in mind that the data was strongly overlapping, and that makes it very complicated to find a good rule how to split it. And that is also reflected in the trees. So this is a single tree, and there are 4 more of those that are used to make the decisions what class each pixel belongs to. And the effect, when we run these, we have the output of the first random tree. No, this is the full classifier. And then we can see 2 of the trees here. Each tree does maybe not do the best performance, but if you combine them, it makes more and more sense. This one looks more like the k nearest neighbor, but yeah, it kind of makes sense, I would say. But this is also a little bit an art how to select these trees. I have seen example where people do segment roots in radiographs with the help of tree-based segmentation. But the problem for them was that they had too little training data, and in the end, it was overtrained, too specialized for a few images, and they couldn't generalize it to a greater collection of images, which was a pity, actually. So we have now looked at very many different ways to process the data, and the question is how we can put them together in a reasonable way. And for that, we can use something called pipelines, where you have different transformation and segmentation steps until you reach the final result. Until now, it was just some scripts where we had some piece of code, and changing codes on the fly to do much testing can be a bit inconvenient. And the pipelines has the purpose that you, in principle, with the help of an array of function names or tasks, you can easily program or parameterize the workflow. So in scikit-learn, there is something called a pipeline, and it has a lot of different processing units. Right now, we are getting the robust scaler, so it's in principle just normalizing the data. And here we have our pipeline, which consists of, so this is just a label, and the scaler, and then we can run the data through that. Nothing special is happening here. Then we can add another line here. So in principle, what you do when you produce a pipeline is just that you add more and more rows into this array, and that gives you the workflow. And that can be more easily also saved in files, and it make to have a basic framework that helps you to evaluate different combinations. The quantile normalizer just reorganizes the data a little bit more, making it more efficient. So you can see here that it's the first data is you have some data which is very narrow, some is skewed towards the negative values, one is actually on two sides of the zero. And by the quantile, you scale everything so that it lands between 0 and 1, which, as we saw with the k-means, that we needed to normalize the data so that everybody were within a given range. That's the kind of effect we want to achieve here. And in this case, when we normalize it, we should, in principle, try to fit it around the 0. I think it's plus minus 1 is the normalization step. Then we can also add a line of polynomial features. So we want up to second order polynomial features that would give you more data to test or to increase your feature vector. And then it goes on doing many of these different approaches. And what we can do is, so when we want to use these pipelines is when we want, for example, to put images into different categories. We have the MNIST data set. Could also be that we want to put different categories like cats and dogs, cars and boats, etc., on the images. And in this case, we start to build a pipeline around the MNIST data. We have 8 by 8 pixel images and 50 of those that we load from this data set. And here we then, first step is we load the input data, then we flatten it so all the pixels comes as a long string, and then we normalize it so all values are more or less around 0. And then we try to do a nearest neighbor classifier to identify which numbers belong to what. And you can see here the pipeline is still just a list of tasks where you put in what you want to do in the second one or parameterize it as you would like to have it. So let's try this. We put in these digits and ran it, prediction, and tested the accuracy score. And we got 100% accuracy on this data. And looking at the confusion matrix, there is no leak whatsoever. And you probably already can assume what is going on here. because, and also looking further on, we have precision recall is perfect. All the scores are fantastic. So something, either it's a fantastic algorithm that we have built, or we did something wrong. The question is what? Do you have an idea?
We have used the same training data as test data.
Yeah. So if we would test some other digit-like image, this one, and say that it should be, actually it's a modified 9. And then this model predicts that it's a 7, so it does some wrong. And the problem is that we have used the same data, and that's kind of a initial problem when people start doing training and testing their model. Is in principle what you need to do is you have your training data, and during the training you should validate, and the validation is just to test between the iterations, how do you perform in this current iteration. And finally, when you want to test the quality, you need yet another test set, and that is a test data which produces then the quality measurement. So there was this is kind of the crime in machine learning that you should avoid. And of course, it requires that you have even more data, but a typical, you have to do some kind of typical split, and mostly you want a lot of training data, some validation data, and not so much. So one split would be 70, 20, 10, but depending on what kind of task you're doing, these values may slide a bit. So go back to the pipeline again. We can try putting also a regression in the pipeline and see what we can do with that. Let's load the digit data again. In this case, we have 50 images for training and 450 for validation. This is a little bit unusual split, but let's do it. So here we bring in the flattening, normalization, and then we do a k-nearest neighbor regressor, which is a little bit a special variation of the k-nearest neighbor, and see what happens. And it seems like the output looks very much like it's actually splitting out nice numbers. And if we run it, we can look at the mean squared error or the average absolute deviation and see what happens. And the mean squared error is pretty good during the training, but during validation there is some leaking into different classes, which could be expected because we had a very small training set, and therefore we will get some more misclassifications. But the main idea is still that it gets most of the numbers right. And then we can increase the number of neighbors and see what that does to our segmentation or classification. And in this case, it looks not so convincing. So it can be even more. It can even be confusing to increase the number of neighbors. And now to come back to the pixel segmentation. So we come back to looking at some of our images that we had before. We have this mitochondria segmentation, which is a pretty messy image actually. And we saw before, was it last week, that the single threshold didn't do very well at all because all the structures have more or less the same gray levels, and also the signal to noise ratio is not really ideal. Filtering did something, but it didn't do the whole story. So let's try some other ways. So we have here, we try with decision trees, random forests, regression, and in the end, I'm going to show a little example of using neural network, so-called UNet, to do the segmentation. Our training data, our image, is this one, and we also have a mask for it. And let's see, we split. We have a training image, which is the left side of the image, and we had validation mask, which is the right side of the image. So it's just a split in the two parts. And let's see how it performs. Ideally, at least the training image should be good. So let's try some kind of regression tree that does some kind of segmentation, and looking at the training image, here is the mask, and this is what the tree delivered us. Not really convincing. We still have a lot of misclassifications. And if we look at the whole image, so this part was the training part, and this part was the validation part. So this one didn't perform very well. It did equally bad on training and validation data. So let's try something else. Combine k-means and a random forest. So let's get a bit wild. We also have added here x and y coordinates. And the k-means should be a clustering between intensity values and positions. And then we let the forest use these clusters for afterwards for the segmentation. This one actually look pretty well on the training data. That is a pretty good match, I would say. However, if we go beyond into the validation data, it loses its understanding pretty soon. And my guess is that in this case, the coordinates are so far off that they will actually downgrade the result. So that wasn't really a good choice. Then we can add some polynomial feature as well, see what that does, and using a random forest instead, and no clustering. Yeah, so this is playing around, seeing what happens. And in this case, the prediction mask again looks really good. But the problem is that somehow it can only extrapolate into the region that has an overlap between the two, the validation and the training data. The rest is completely black. So also that one didn't do very well. Then we can add some gradient filters to identify and smoothing to see if that helps. And that actually starts getting, oh, I got a little bit too much here, starts getting into something that starts looking good. So this may be the right way. So what we have done is actually adding neighborhood information into this segmentation, which we didn't have before. And that seems to be a good choice. That one shouldn't be there. It should be in the skips, sorry. So anyway, with the help of these pipelines, we have the possibility to easily test and bring in new approaches without the whole overhead of moving data between different functions, etc. So it's a convenient way to work. So now let's make it bigger again. The last part today is like a very, very quick crash course straight into neural networks. This is a huge topic, and I can only scratch a little bit on the surface, but in principle, when we're talking about AI and learn and neural networks, it's this kind of structure that is talked about, where we have some input nodes that is fed with information, and then in these nodes there is some computation done, and the output of each node is forwarded into a next layer of nodes, which does yet another calculation, and the combination of all these layers and nodes results in an answer afterwards. Could be that it just tells which class it is. We saw very in the convolution, now in the filtering lecture, we saw one example that could get a speed sign, and afterwards you could tell which speed is recommended. That could be one output. Could also be that we want to segment a whole image, so then we bring in the image here and the input layer, and out comes the segmentation result. For this perfect concept, something called a UNet was developed, and it consists of big blocks. Each layer here is actually a huge set of convolution kernels probing different orientations, different sizes, and the special thing about the UNet is that it does all these convolutions, weights the outputs, brings them to the next cascade of images, and then it does a downsampling. So it's actually also working on scales. And it does that a couple of times, and then it goes back, and then it upscales, and finally you have the segmented image. And I think this was one of the greatest inventions towards segmentation using machine learning. Meanwhile, there are other models, but this one was really a starting point for doing this. And it came also with the development of using graphic cards for processing, because before that it wasn't computationally feasible, because you needed so much computational raw power to do this. So let's build a little network, and same concept. Here we now have some convolution layers, and I'm actually not going to go too deep into it, but we have the building blocks, in principle, a couple of convolution layers, and we have the downsampling, and then we, at some point, we go back up again to build this network. And looking at it, the output summary is what it looks like here. It also tells us, if I can scroll up, no, I can't, how many parameters that are tuned in this network. I think it's a couple of millions or something like that. So it's pretty many parameters that needs to be trained and tuned. And it's not only the weights between all the nodes, but it's also the shape of each convolution filter that is in this network. So it's a pretty big optimization problem that needs to be done, and that's also why it takes so much computational time to compute. So this is what the model would look like, what we have built here. And yeah, let's see if I can scroll it. Yeah, nee. It's not meant to. Okay, anyway, it will go up and down. It actually flips upside down, so it's not a U, it's a U on the head. And then we need to, again, have some training data, and this is a quite big problem, so we reduce the data to processes in shorter time. And well, I had a little bit problem with this example, to be honest. Yesterday evening, when I wanted to run it, I probably did some updates, and all of a sudden my kernels crash, so I couldn't actually finish this example. It worked last year, but now, thanks to updates, it doesn't, which I apologize. Also, that is the reason why I couldn't provide the updated lecture note, so you're still on the 25 lecture notes. I'll try to fix it the next days, and hopefully I will have a working example and also the 26 lecture notes. Anyway, I can show some glimpses of what's meant to be. In this case, if we run the untrained network, you can see that it's more or less just like some kind of convolution blur, which we can expect because the network just runs a lot of different convolution kernels and no real processing of the data that would lead to the segmentation. Another thing is, in this particular case, I only use one single image, which is not a good idea, but that's more a question of having something that goes through quickly, because once you start running these models, you can sit hours, particularly on a laptop, before something comes out. So I had to reduce the data set quite a lot, and also the kind of optimizer and loss function. Everything costs computational time, and that's why I have reduced it quite a lot. So ideally what you should have is hundreds of these microscope images labeled to run the training and validation, and afterwards also the test. But that would take an enormous amount of time, which we can't do in this lecture. There are also some training functions. We work when we do these training iterations. We check the quality, and that is done towards different metrics. So we have, for example, binary accuracy, if the segmented pixel is what we expect, and then sum it. There is also the mean absolute error. We can also use something called DICE score, which is this expression based on true positives and false positives, false negatives. And that is a quite common metric for the training. The training would look something like this, that we run these error function, look at these metrics. We can see that the training error is decreasing, also the validation error is decreasing. So this is kind of the style that we would expect from this kind of training. And yeah, as things crashed, I get, in principle, just everything is a mitochondrion, which is not. So that was the thing that happened yesterday. And we also get a lot of overfitting, and then it's the question how to improve this model. And that can be done by setting different optimizers, the different training metrics, and also training rate, how quick the model should update. And yeah, then we can get some curves again. And yeah, this one didn't segment anything. Yeah, so I was in a bad condition yesterday. I hope to get you a working example the next days, so that I will update. This was now a very small model and also trained with limited and not ideal data, but it was more about showing the workflow and the building blocks that you would need. Another model that has come up in recent years is the SAM model. SAM stands for Segment Anything model. And it's a quite nice model, but it requires that you give it some seed points for the segmentation. And let's have this mammogram again, where we have the background, breast, and some kind of tumor. And the notebook I did this is actually also in the repository if you want to play with it. What I did, I just marked some points in the background. I marked some points in the tumor, and out came this segmented region. So it's pretty amazing actually how it works. And yeah, the example on Google's homepage is that you have a dog and you can just click 2 points on the dog and you get the dog marked up. It works on some categories of images, so like the dog is a given one. Also medical images, it works pretty well. I tried it on my material science examples and it failed completely. So it hasn't seen this kind of data and cannot handle it. Maybe meanwhile it can, but when I was doing this example, it wasn't able to do anything. Yeah. So in principle, if you compare the unit and the SAM, is unit is a convolutional encoder-decoder architecture, and it must be trained using a labeled data set. And with that, you can really target a specific problem and have good quality. SAM is already a pre-trained model. It's a large language model, actually. And it already has all the training data in itself, so you can more or less just deliver the data. Sometimes you can do some tweaking on it, but you can get the result in principle in a single shot, which is interesting. A problem is that you have to guide it with some user prompts. So it requires some interaction. Meanwhile, there are also some approaches to provide these user points, but that's so it's a cascade of tasks in that case. And yeah, that brings me to the end of today's lecture. Next week, I'm going to talk about, let's see if I get it right in the order, but I think I'm going to talk about metrics, what we can do with these segmented items, and then starting producing the data that we want to quantify, actually. So that was all for today, and thank you.